Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today in this tutorial I am going to cover the paper Feature Reinforcement with Word Embeddings and Parsing Information in Neural TTS. So TTS is text to speech. So this paper is by Hu Peng Ming, Lai Wan Guo and Frank Song. This paper is from Microsoft China, and warning is this paper does not include any reinforcement learning technique. This is just plain neural network based text to speech system along with informations like word embeddings and parsing information. So overview of the paper we are going to cover in this tutorial. Then we will see what is the neural TTS system. Then we'll see the proposed approach in this paper, and we'll see what is the dataset used, and finally we'll see some experiments and results. So in the overview we see that this paper uses this feature reinforcement techniques. Basically feature reinforcement technique is not any technique, it's just about how do you add different features as a reinforcement signal to the model to boost up the performance. And in this method they use the sequence to sequence based neural TTS system, and they add different feature to enhance the accuracy and to enhance generalizability. And this model uses multiple encoders. When I say multiple encoders, so each encoder will encode some signal, and each signal will be some sort of input feature to the model. And we see that these multiple encoders process information at different level, like for example word level, utterance level and phoneme level, right? And as I said, the three levels of text information like phoneme sequence, pre-trained word embeddings and grammatical structure of sentences from parser are going to go as an input to the neural TTS system. So basically we are covering from granular level like phoneme level to the large level like utterance level features. And this model doing this multiple encoding or adding these sort of features is going to improve the generalizability, and is going to the problem of out of domain text can be reduced in this technique, I mean in this way. And they show that this system, this neural TTS system built in this way gives better robustness to out of domain text, and the synthesized quality of the audio signals are nearly as good as the human level or recording level uh, recording quality. So first we'll see what is neural TTS system, then we'll say actual proposed approach in this paper. So what is neural TTS system? So basically this neural TTS system is nothing but some sort of sequence model where this, if you remember, this picture is exactly the Tacotron 2 paper. So basically they have an encoder which actually takes a phoneme sequence and adds multiple layers of convolution and LSTMs and encodes the features of phonemes, and then we apply attention mechanism on that by LSTM layers hidden activities. Then we'll use the decoder. So basically decoder is some sort of again LSTM, and it tries to predict sequence of mel specific mel features, and from that we are going to feed that mel features as an input to wavenet, and the wavenet decoder will wavenet vocoder basically generates a waveform. Instead of wavenet we could plug in graphene limb synthesizer also. So this is the baseline neural TTS system, and this is going to be used as a baseline system, and whatever improvements they are going to do in this paper is going to be on top of this system. So basically they are using the same Tacotron system, but it's not exactly Tacotron system, because the Tacotron system written in the paper, the Tacotron 2 paper, basically uses the character sequence or the grapheme sequence as an input, but in this paper they are changing the graphemes of phonemes. That's the only difference, I mean compared to that architecture with this architecture. And if you see, so what are we interested is we are interested in predicting the speech features given the inputs in phoneme sequence. So X you can think of as a phoneme sequence, and Y you can think of as sequence of mel filter or MFCC features, for example. And the audio encoder and decoder has their own parameters. So theta basically consists of two different parameters. One is an encoder parameter, another is a decoder parameter. And what we are trying to optimize is a mean square error loss, and we can describe that mean square error loss over here. So where we have difference between the ground truth MFCC sequence or mill frequency yn cap, and I think this is the mistake in this paper there. I think so, because this yn is the ground truth speech feature, right? So if this is a feature, so basically you can think of it as an MFCC feature, and the subtraction you are doing, so basically when I say subtraction, basically you are doing the prediction means you are doing regression, right? So if you are predicting the features yn, then that should be difference between the yn hat and yn hat and yn normal yn. So basically this probability should have been replaced by yn, which is basically the output feature sequence or output speech feature at that particular time n, and then you could take the difference between those two feature vectors and compute the mean square error loss. I believe this is the mistake, but I just have to check it once. So this is the mean square error loss you want to calculate, and you want to minimize this mean square error loss, and the parameter you are going to optimize by minimizing this mean square error loss is theta, and it's the both encoder and decoder parameters. And n is the total number of audio and text pair you have in your database, and maybe it will be hundreds of thousands of speech and text, parallel speech and text pairs. So that is the baseline neural TTS system. And then we'll see the system they have, as I said initially, what is the contribution of the paper is to improve the tachotron system to get more generalizability and to capture this out of domain paper, out of domain text data, means to generate good audio for out of domain text data also. So basically they are using technique of feature reinforcement, where you add multiple features at multiple scale. So you have features at phoneme sequence already, so you want to add features at the level of word, and you want to add features at the level of utterance. So for example, if you have word sequence, you could take a pre-trained model of pre-trained word embeddings maybe, then you can feed that as input along with the phoneme sequence also as an input. For example, this becomes like a sort of multimodal. It's not a multimodal, it's like sort of two different inputs you are passing. So you have a phoneme sequence here at the bottom, and you have another one encoder here. So this encoder consists of phoneme embedding layer, it's basically embedding layer. They have a convolution, and then you have bilateral layers, right? Now you have another encoder which is basically going to take the upsampled version of word sequence, because you want to make sure the sequence of features you predicted, the bilateral layer of this encoder and sequence of hidden layer vectors you predicted this encoder should be same, because you want to concatenate them. So that's why we do upsampling of this word sequence to match the phoneme sequence length. Then we apply the same word embedding layer and then convolution of the esteem layer. Finally, we concatenate a feature representation at each time, and then we are going to pass it to attention mechanism. So this is going to be exactly similar to this, actually similar to this part, but the thing is they have two different encoders right now, because we want to add multiple layers of feature information. So basically we are adding word level information along with the phoneme level information. So this is one thing. And next, what we are going to do is we are going to construct another system which is basically phone plus grammatical structure. So the grammatical structure is a parsing tree basically. So you could get the Stanford NLP parser, for example. If you use, you get the parsing information. So that is going to go as an input to the dense layer and then convolution layer. Then the phoneme sequence also goes as input to phoneme embedding convolution layer. And then we finally pass it to BLSTM and the attention mechanism. So right now we have two different systems. One is the word plus phoneme sequence system, another is grammatical plus phoneme sequence system. Now we want to combine all of them together. That is the last system. So where you have information from phoneme sequence, you have information from upsampled version of parsing information, then you have information from upsampled version of word sequence. Then all of these three features are going to go as an input to the layers, the system basically. Then you have LSTM layer. So here is where the trick is. The encoder is not one, it's a multiple encoder, like 3 different encoders in this paper. So that is the whole architecture, whatever they have proposed in this system, and then finally remains the decoder remains same, and the vocoder is remains same, the same wavenet vocoder. And coming to the data set, so the data set they have around 19 hours of speech spoken by US female speaker, professional US female speaker. Then they have transcripts in general domain, and speech waveforms are single channel and 16 kilobytes, 16 bit and 16 kilohertz sample. So coming to the experiments and results, so first one is they have a baseline system where we have in-domain text transcript. The MOS score for the recordings is 4.51, which is good. I mean, good in the sense this is the baseline, you have the ground truth. Then the model which they have built in this paper, the baseline model, is actually almost close to the recording level, like 4.41, which is really good, right? Then coming to the experiments, that is this is for in domain text transcript, which is basically it's sort of if your training data is in news domain, your testing data is also news domain. But the question is, what will happen if I feed something related to sports, or sorry, for example, let's say story, or let's say politics, right? So what will happen? So those are the ones which are going to have out of domain text. So for that, so the paper, whatever paper they have written, so they have done different experiments. So if you use only phone as input, for example, for the out of domain text transcript, if you use phone as the input, the MOS score you are going to get is 4.17, which is less than 4.41, which is actually the actual MOS score of the in domain text transcript neural TTS. Now they have showed that if you add phone sequence plus word features as input, then you get a little bit improvement over the only phone as input model, right? Which becomes like 4.19, which is good. Now if you add phone plus parsing information, you get again a little bit, not that much, a little bit information, a little bit improvements over the only phone as input model. Now if you add all these three models together, like word plus phone plus parsing information, then you get good improvement, like from 4.17 to 4.33, and which is almost close to the recording means the ground truth MOS score, right? It is 4.33 and 4.44, which is a good thing. And yeah, that's all for this paper, and thank you so much for watching this video. If you are not subscribed to my channel, please subscribe for more content. Thank you.